Hello everyone, welcome to our ViLEG program. Here we will learn about various spectroscopic techniques. Previously, the UV visible spectroscopy and fluorescence spectroscopy were demonstrated. Today we are going to learn about IR spectroscopy. In IR spectroscopy, we use infrared light of the electromagnetic radiation to probe a molecule. So, what happens when we shine infrared light upon a molecule? Actually, infrared causes vibrational excitation in a molecule. So when frequency of infrared radiation matches with the difference between two vibrational levels of a bond, the molecule will absorb the infrared radiation of that frequency and will undergo vibrational excitation. Let's consider vibration in a simple diatomic molecule. The vibration in it is similar to that of a simple harmonic oscillator. When we displace the atoms from equilibrium position, a restoring force will act, which will bring back the atoms to their equilibrium position. And the restoring force is given by Hooke's law, which is F equal to minus Kr, where R is the distance between the two atoms and K is a proportionality constant. We know that force is actually negative rate of change of potential, which is minus dV by dr. So from that we can have V equal to half Kr square. And we know that it is a quadratic equation and it gives us a parabola, which is shown in green curve here. And the horizontal lines shown here are actually vibrational energy levels, which are actually quantized. And the vibrational energy levels are given by vibrational quantum number, which is represented by V or sometimes by N, which can have a value of 0, 1, 2, 3 and so on. The vibrational energy of these vibrational levels is given by E equal to N plus half h nu. However, in harmonic oscillator model, the molecule does not dissociate regardless of the amount of energy provided to it. So it is actually not possible for a real molecule. Therefore, movement of a real molecule is not perfectly harmonic, because as distance increases, restoring force weakens, and for large amplitude vibration, the atoms fall apart. That is, the molecule is dissociated. Such an oscillator is known as an harmonic oscillator. And PM Morse suggested an empirical expression for the potential energy of an anharmonic oscillator, which is shown here. When you plot this potential, it will have a form shown in the blue line, and we can see that the potential actually matches with the harmonic potential at lower vibrational energy level. However, when we move to higher vibrational energy level, the Morse potential actually deviates from the harmonic potential and reaches an asymptotic limit. And the energy difference from this point to the minimum of the potential energy curve is known as spectroscopic dissociation energy. However, the molecule always doesn't rest at this level. It is always placed at V equal to 0 or higher level. So from this point to V equal to 0, the energy is equal to half h nu, and when we will add half h nu to dE, we can have d0, which we can obtain spectroscopically. So now let's move to instrumentation. Here we have an IR source, which can be a nernst glower or nernst filament or a glower source. Then there is a beam splitter, which actually splits the beam into two halves, and then the beams are sent to a fixed mirror and a movable mirror. Then the beams are reflected back from the two mirror and meet at the beam splitter. There we can have interference pattern, and depending upon the phase difference between the two incoming beams, we can have either a constructive interference or a destructive interference. So we obtain a complex interferogram which contains all the information about the IR frequency, and which is then passed through the sample, which absorbs the IR radiation, and then finally the infrared radiation reaches the detector. Here we obtain a complex interferogram, then it is Fourier transformed to IR spectra. So we can have IR spectra in all the phases of matter. So in our lab, we use Vertex 70V for recording of IR spectrum. For solid spectrum, for solid sample, we have a pellet holder like shown here, and this is a sample pellet. Then for liquid samples, we use liquid cell holder as shown here. Then for gaseous sample, we have multipass gas cell. So IR spectrum can be recorded both in absorbance and transmittance mode. However, transmittance mode is mostly preferred. So in our lab, we have recorded various compounds, and here are a list of compounds whose IR spectrum have been recorded in our lab. So let's have a look at the spectrum of cyclobutanone. So this is the cyclobutanone molecule. So when we press the scan button, we can see the recording of its IR spectrum. So when the molecule transmits all the infrared light and doesn't absorb, it has a transmittance value of 1. However, when it absorbs infrared light, we can see a dip in the spectrum. So we know that a molecule with n number of atoms has a total of 3n degrees of freedom, out of which 3n minus 6 is the vibrational degrees of freedom for nonlinear molecule, and 3n minus 5 is the vibrational degrees of freedom for linear molecule. So as cyclobutanone is a nonlinear molecule having 11 atoms, it has 27 degrees of freedom. Here it can have CC stretching frequency, cis double bond O stretching frequency, or it can have CCC bending modes. Here the carbonyl stretching frequency occurs at nearly 1789 centimeter inverse. So from here we can obtain the force constant of C double bond O. So for that, here we have to put the stretching frequency, that is 1789.6 centimeter inverse. Then we have to select the atom. Here atom 1 carbon, let's choose atom 2 which is oxygen. And then while we press the calculate, we can see that the force constant is 1294.54 Newton per meter, which can be obtained using this equation, which is k equal to 4 pi square mu nu square. Here nu is the frequency. However, for the wave number, we can have 4 pi square mu mu nu bar square c square. Okay, so let's have another molecule. So let's set it to transmittance, then set compound as cyclopentanone. So we have another ketone. Then let's hit the scan button. So here is the IR spectra of cyclopentanone, and cyclopentanone has a total of 14 atoms. So it will have 36 number of vibrational degrees of freedom. So here we can see the various modes, and the CO stretching frequency mode appears near 70-50 centimeter inverse. Here the CS stretching mode occurs near 3000 centimeter inverse. So let's find out the peak position of this CO. So it's around 1748.8 centimeter inverse. Let's find out the force constant of cis double bond O. So we have to put the wave number here, that is 1748.8. Then we have to select atom 1 and atom 2. Then we have to press calculate. So here the force constant is 1236.19 Newton per meter. So using IR spectroscopy, also we can find out the anharmonicity constant, also the dissociation energy, using the equations provided here. So hope you learned about IR spectroscopy. Thank you.